right, welcome back. Today we're going to be starting Unit 9 out of 10 total units. We're slowly getting there. And this unit is really a mix of just three topics. Differential equations, which is definitely a big deal. I can pretty much guarantee that one of your 6 free response questions on the AP exam will be about differential equations, and probably taken from several of the little sections we're going to look at over the next couple days. And then the other two topics, inverse trig and something called L'Hopital's rule. Basically, I just needed some place to put them, so I stuck them in this unit. So for the most part, these are just three unrelated topics that we just need to deal with. The differential equations is what we will certainly be spending most of this unit on, but all topics will show up in some form on the AP exam. We're going to skip over section 5.6 for right now, because section 5.6 is all about using differential equations, and I think before we talk about using them, we need to talk a little bit about, well, what they are, how to solve them, and all that stuff. So we'll come back to 5.6 tomorrow and next day. But we're going to start with section 5.7 about differential equations. I know I've defined a differential equation before, but I want to define it one more time. A differential equation in x and y is an equation involving x, y, and derivatives of y. A differential equation in x and y is an equation involving x, y, and derivatives of y. Oops, sorry for the lag. And an example of a differential equation might be something like y double prime minus 2xy prime equals the cosine of x. Our goal with these differential equations is to find a function y of x that satisfies the equation. So looking at the example that I gave you, my goal would be find some function so that if you do the second derivative of that function, minus 2x times the first derivative of the function, when you plug all this stuff in, it simplifies down to just cosine x. As I mentioned before, when we started looking at these back in section 4.1, in general, differential equations are very difficult to solve. There are entire college courses devoted to different methods for solving differential equations. We're just going to stick with a few in very special cases in here. But if you do go on to take more math in college, you'll probably deal more with differential equations then. So the first thing we're going to look at is, okay, maybe we don't know how to solve a differential equation yet, but we can figure out, is something I give you a solution? You don't have to copy this down, but going back to like middle school, before you knew how to solve regular equations, if I gave you something like this and asked you, is x equals 2 a solution to that equation? Let's pretend you don't know anything about solving equations. No add 3, divide by 2, nothing like that. How could you see if 2 will be a solution or not? Well, before you knew how to solve an equation, you would have just plugged in 2 to see if the left side wound up simplifying down to 5. We're going to do something similar with these differential equations. First example, given the differential equation x y prime minus y equals x squared, we want to determine if y equals 3x plus x cubed is a solution. Given the differential equation xy prime minus y equals x squared, I want to figure out if y equals 3x plus x cubed is a solution. I'll make the video pause so you can get that in your notes. We don't know how to solve a differential equation like this, but that doesn't matter. Just like when you were in middle school before you knew how to solve equations, it didn't matter that you didn't know how to solve this. You could still figure out if 2 is the solution by plugging in. I'm going to do the same thing. I'm going to go and I'm going to plug in my y. However, there's a place for me to plug in y prime, which means I'm going to need to first figure out y prime. Y is 3x plus x cubed. Y prime is just its derivative, and the derivative of 3x plus x cubed is 3 plus 3x squared. I have everything now that I need to be able to do some plugging in. I want to look at the differential equation xy prime minus y equals x squared. I'm going to plug in. I'm going to say x times 3 plus 3x squared minus 3x plus x cubed. I don't know if this actually equals x squared. I'm going to say maybe equals x squared. And my goal now is just to do some simplifying on the left side to see if this thing simplifies down to x squared. I'm going to get 3x plus 3x cubed minus 3x minus x cubed. I want to see if that equals x squared. Let's see, the 3x's cancel. You're getting 2x cubed, which does not always equal x squared. If this was a solution, the left side would have simplified down to just x squared. And because it simplified down to something that's not the same as what's on the right, my conclusion is no, it is not a solution. All I'm doing here is plugging in and then simplifying. If when I simplify, I get what's on the other side of the equal sign, then yes, it's a solution. If I get something different, no, it's not. Make sure this is in your notes. Let's do one more like this. Is y equals 1 over x squared a solution to x squared y double prime plus 5xy prime plus 4y equals 0. I want to figure out if y equals 1 over x squared is a solution to that complicated looking second order differential equation. Please take a moment and calculate your y prime and y double prime and send those into Edpuzzle. We're not looking at the differential equation right now. Truly just straight derivatives. Find the first derivative and the second derivative of 1 over x squared. I think I'm going to have an easier time if I rewrite this with a negative exponent. So y equals x to the negative 2. Y prime equals negative 2x to the negative 3, or negative 2 over x cubed. Y double prime equals 6x to the negative 4, or 6 over x to the 4th. We have everything we need, so now we're going to plug in. I'm going to get x squared times 6 over x to the 4th plus 5x times negative 2 over x cubed plus 4 times 1 over x squared, and I want to see if that ends up simplifying down to 0. Take a moment to do some algebra on the left side and tell me what the left side gets simplified to. So this is 6 over x squared minus 10 over x squared plus 4 over x squared maybe equals 0. Yeah, it does. 6 minus 10 is negative 4 plus 4 is 0. 0 equals 0. And that tells me, since the left side does equal exactly what I had on the right side, yes, it is a solution. I'll pause so you can make sure this is all in your notes. Next thing we need to look at, solving differential equations. Solving differential equations, as I previously mentioned, in general, this is very difficult to do. We are just going to look at some very special cases of differential equations in here that we can deal with. And if you go on to take more math classes in college, you'll see more there. There are 3 techniques we're going to look at in this unit. The first one we've already seen, just straight integration. And that method works when we have something in the form dy dx equals something with just x's. We'll do one of those in a moment. It won't be a big deal. Second method, which is what most of this video will be spent on, is a method called separation of variables. And we can use that method when we have dy dx equals the product of something with x's times something with y's. We'll deal with this in just a moment. Third method, which we'll look at next week, involves drawing things called slope fields. And this is a very different approach to differential equations. This is a graphical technique for solving differential equations. And we're going to see with that method, we're not actually going to get a formula for our solution, but we'll at least get a picture of what our solution looks like. We'll deal with that method next week. Make sure these 3 methods are in your notes. So the first method we're going to deal with is just straight integration. And again, as I said, this is when we have something in the form dy dx equals something with just x's in it. I want to solve the differential equation dy dx equals x over 1 plus x squared. Well, all you need to do, because this thing just has x's in it, is we just have to integrate. What has a derivative of x over 1 plus x squared? Well, whatever the antiderivative of x over 1 plus x squared dx is. I think you could probably handle integrating this. You should be thinking use substitution. Take a moment and go integrate that, please. And you know what? When you're done, send the answer into Edpuzzle. So to be able to integrate, I need a u substitution. I'm going to make u the denominator. Its derivative du is 2 times what I have in the numerator. So I'm going to stick a 2 in there and a 1/2 out front. This is 1/2 times the integral of 1 over u du. Y equals 1/2 times the natural log of the absolute value of u plus a constant. Y equals 1/2 times the natural log. I'm going to drop the bars because this u is always positive. Natural log of 1 plus x squared plus a constant. There's nothing new here at all. I wanted to show you one just to kind of make our list of methods complete, but that's really all that I want to say about this. You've seen this before. This is nothing new. What we're now going to turn to, that second method, separation of variables. Definition. A separable differential equation can be written in the form dy dx equals something with x's in it times something with y's. A separable differential equation can be written in the form dy dx equals something with x's times something with y's. So for example, dy dx equals x times the sine of y is a separable differential equation because I can write it as something with x's times something with y's. What about this one? Dy dx equals xy minus 2y. This is not something with x's times something with y's, but could it be written in that form? Could we separate our x's and y's? Is it separable? I think it is, because I think we could rewrite this as dy dx equals y times x minus 2, something with x's times something with y's. One more. Dy dx equals 2x over y. That's separable because we can say it's 2x times 1 over y. These are all examples of separable differential equations, and these are all examples of things that we will learn how to solve in the next 15-20 minutes or so. I'm going to pause so you can make sure this is all in your notes. To solve by this method called separation of variables. And I think, whoops, sorry, let me try that again. To solve by separation of variables, what I think I want to do is give you the steps as I show you an example. So the example we're going to look at here is we're going to solve the differential equation dy dx equals x squared over y to the fourth, which is separable because I can say it's x squared over y to the fourth or something like that. Step number 1, I'm going to do some rewriting here. First of all, this dy dx symbol, I'm actually going to treat this like a fraction. I'm going to treat this like the fraction dy over dx. What I'm going to do is use some algebra to rewrite this problem so I have the x's and dx on one side and the y's and dy on the other side. I need to rewrite this so the x's and dx are on one side and the y's and dy are on the other. My first step is going to be to rewrite this problem, separate things, so I get the x's on one side along with the dx differential, and the y's on the other side along with the dy differential. Well, again, I'm going to treat this as a fraction, dy divided by dx. I think all I need to do in this particular problem is cross multiply. And I can say y to the fourth times dy equals x squared dx. And this is my separation step. I have separated my variables. Step number 2, we're going to integrate both sides. Step number 2, we're going to integrate both sides. So I'm going to get the integral. So let me come back up here. I don't want to use up the room down there. I'm going to integrate and get the integral of y to the fourth dy equals the integral of x squared dx. When I integrate y to the fourth, I get y to the fifth over 5 plus a constant. When I integrate x squared, I get x cubed over 3 plus a constant, different constant. Let me call them c1 and c2. And actually, there's no need to have both of those constants. I could just kind of move this c1 over to the right side, c2 minus c1, a constant minus a constant is still just a constant, different constant, but still just a constant. So instead, why don't I just say this is y to the fifth over 5 equals x cubed over 3 plus c, because I can just group the constants together in one thing. It's a different constant, but still just a constant. And I think in general, when I move forward and do these problems, I'll always put the constant on the side with the x's, not on the side with the y's, because I'll assume I could just move that over to the side with the x's. There is one more step. What I'm going to do now to finish this is solve for y to create a function. Solve for y. I guess we'll say if possible, but I'm pretty sure most of the examples I show you it'll be possible to create a function. I want to turn this equation into a y equals equation. Well, to do that, I think the first thing I would have to do is multiply everything by 5. When you do that, you get y to the fifth equals 5/3 x cubed. And now 5 times a constant, still just a constant. Different constant, but still just a constant. So I'm going to say plus c. It's a different constant, but it's still just a constant. Now, to undo my fifth power, I need to do the fifth root. I need to take the fifth root of the left side and the fifth root of the right side. I'm going to get y equals, now I need to take the fifth root of the entire right side. I'm going to say 5/3 x to the third plus c, and notice that my constant is underneath the root. You're not allowed to like separate a fifth root and say, let's do the fifth root of this, and then the fifth root of that. If we could just say a plus c at the end, but that's not the case. We're taking the fifth root of the entire side. That idea doesn't distribute to both of those things, so we're going to leave our answer like this. Please make sure this is all in your notes. All we're going to do for the rest of the video is look at a whole bunch of different examples of this separation of variables method. My goal is really just to show you as many different varieties that tend to show up on the AP exam. And I think we're actually going to see the integration shouldn't necessarily be the tough part. The tough part's actually usually the algebra at the end to make sure we're getting a function. So let me show you a bunch of variations on this. Not even variations, just examples. We're going to solve the differential equation. Y prime equals x times 1 plus y. Well, first of all, of course, y prime is dy dx, dy over dx. I think I can separate this by multiplying both sides by dx and dividing both sides by 1 plus y to get dy over 1 plus y equals x dx. Again, I multiplied both sides by dx, put the dx over here, and then divided both sides by 1 plus y to get this. I'm now going to go and I'm going to integrate. I think the right side should be very easy, but I think the left side is going to require a u substitution. To integrate the left side, what's u and what's du? Well, I think my u over there is 1 plus y. Its derivative du is just 1 dy, so the left side is just du over u. The right side is just the integral of x dx. I'm going to integrate. When I integrate du over u, I get the natural log of the absolute value of u. I'm not going to include the plus c because I'm going to stick that on the side with the x's. When I integrate x, I get x squared over 2. I'll put my plus c over here. Again, we really do have constants on both sides. Why don't I just subtract the 1 from the left and put it on the right and just rope it into one bigger constant? This is the natural log of the absolute value of 1 plus y equals x squared over 2 plus a constant. I'm done with the calculus. The rest of my work is trying to solve this thing for y. What can I do to get rid of a natural log? To undo a natural log, you need to do e raised to both sides. I'm going to do e raised to the natural log of the absolute value of 1 plus y equals e to this entire side. So I'm going to say x squared over 2 plus a constant. Now, on the left side, my e and my natural log, they cancel, giving you the absolute value of 1 plus y equals, well, on the other side, I've got e to the x squared over 2 plus c. First trick of simplifying I'm going to show you. When we have a sum in our exponent, by our exponent rules, it's kind of like I'm saying that right side maybe came from the problem, e to the x squared over 2 times e to the c, because isn't it true when you multiply two things with a common base, you add the exponents? Why would I ever do something like that? Because e raised to a constant is just a constant. Different constant, but still just a constant. I'm going to say the absolute value of 1 plus y equals a constant times e to the x squared over 2. At this point, I'm actually just going to drop my absolute value bars, and the reason you're allowed to do that is because, well, this constant that's now out front, I can choose my constant to make sure it accounts for whatever sign I had over here. So I'm not really going to have to worry about things like that. Don't worry too much about the bars. All I have left to do to finish this is subtract 1 from both sides. And the solution to my differential equation will be c e to the x squared over 2 minus 1. Please make sure this is in your notes. Next, for the remaining examples, we're going to look at differential equations that have some initial conditions. We're going to solve the differential equation x squared plus 4 dy dx equals xy, and I'm going to tell you that y of 0 equals 8. Don't worry about that for right now. Take a moment and see if you can just separate your variables. Get your y's and dy's on one side, x's and dx's on the other. Oh, and by the way, dy and dx can never be in the denominator. They always need to be in the numerator of our fraction. See if you can do the separation step. I'm going to divide by y, multiply by dx, divide by x squared plus 4. I think I'm going to get dy over y equals, let's see, x, divide by x squared plus 4, multiply by dx. That's my separation step. We're going to integrate. Y is Is it not focused? Okay, now it's a little better. When you integrate, left side should be straightforward enough, but the right side requires a u substitution. What's u and what's du? U is going to equal x squared plus 4. Du, its derivative is 2x dx. So I can make that work with a 2 inside and a 1/2 outside. And this is going to become the integral of dy over y, or 1 over y dy, equals a half times the integral of 1 over u du, or du over u. We're going to integrate both sides. The integral of 1 over y dy is the natural log of the absolute value of y. On the other side, 1/2 times natural log of the absolute value of u. And since that was the side with the x's, I'll stick my constant over there. Let me replace the u with x squared plus 4. And I'm going to get that. Now for some simplifying. Before I try to get the y by itself, where could I move this 1/2? By my laws of, my properties of logarithms, I can take the 1/2 out front and turn it into a power inside there, saying the natural log of x squared plus 4 to the 1/2. Or why don't we just say natural log of the square root of x squared plus 4? Natural log of the absolute value of y equals the natural log of, by the way, this thing is always positive, so I'm just going to drop the bars and say square root of x squared plus 4, plus a constant. I'm going to try to get the y by itself, so I'm going to do e raised to both sides. E to the natural log of the absolute value of y equals e to the natural log of the square root of x squared plus 4 plus a constant. On the left side, I'm going to cancel the e and the natural log, and I'm just going to drop the bars. Don't worry about the absolute value bars with these. I'm just going to drop them. On the right side, I can't completely make this cancel because I still have the plus c in that exponent, but I'm going to use the same trick I used in the last problem. I'm going to say this is e times the natural log of the square root of x squared plus 4 times e to a constant. Well, this becomes y equals, now I can make the e and my natural log cancel, getting the square root of x squared plus 4. E raised to a constant, still just a constant, different constant, but still just a constant. So my general solution to this differential equation is y equals c times the square root of x squared plus 4. Now I'm going to plug in 0 for x, 8 for y, and solve to get my c value. I'm going to get 8 equals c times the square root of 0 squared plus 4. Oh, you know what? You can solve that. Tell me what c equals. 8 equals c times square root of 4 is 2. I think my c is going to be 8, which means my final solution to this differential equation is y equals 4 times the square root of x squared plus 4. Y equals 4 times the square root of x squared plus 4. Next example. Actually, before the next example, I'll make it pause so you can make sure any of this is in your notes if you're missing any parts of that. Let's look at dy dx. Equals 3x squared over e to the 2y. And I'm going to tell you that y of 0 equals a half. Go separate your variables and then stop. Really, I'm just going to cross multiply. I'm going to get e to the 2y dy equals 3x squared dx. And I'm going to integrate. Straightforward, u substitution. See if you can go do your u substitution on the left side. Find your u, find your du, and actually go, you know what, do the u substitution and all that, but actually integrate both sides of this thing. Don't worry about the solve for y part yet. just do both integrals. Okay, so u equals 2y, du equals 2 dy. Sticking a 2 in and a 1/2 out. This is 1/2 times the integral of e to the u du equals the integral of 3x squared dx. 1/2 e to the u, 3x cubed over 3 plus a constant. This is 1/2 e to the 2y equals x cubed plus a constant. I need to get rid of the 1/2. I'll do that by multiplying everything by 2. So e to the 2y equals 2x cubed plus a constant. How do you get rid of an e raised to the? What undoes e raised to the something? I hope you said the natural log. I'm going to go and I'm going to take the natural log of both sides. The natural log of e to the 2y equals the natural log. Remember, again, we're doing this to the entire side. So natural log of all that stuff, the c is ending up inside my natural log. 2y equals the natural log of 2x cubed plus a constant. And dividing by 2, y equals 1/2 times the natural log of 2x cubed plus c. What we need to do now is plug in 0 for x, 1/2 for y, solve to get the c. See if you can do that and tell me what your c value is. Let's see, 1/2 equals 1/2. Natural log 0 plus c. Multiply both sides by 2 or whatever. 1 equals the natural log of c. E to both sides. I think my constant is going to be e to the first, or my constant's really just going to be e. Which means my solution to this differential equation is y equals 1/2 times the natural log of 2x cubed plus e. And there we go with that one. Make sure this is in your notes. Okay, next. Okay, we're going to solve the differential equation. dy dx equals x squared minus 2x over y. And I'm going to tell you that y of 0 equals -3. See if you can separate, see if you can integrate, and then stop. Okay, separating is going to look like y dy equals x squared minus 2x dx. I'll integrate, and actually, neither side requires a u substitution here. Y squared over 2 equals x cubed over 3 minus 2x squared over 2 plus a constant, or 1/2 y squared equals 1/3 x cubed minus x squared plus a constant c. We need to solve for y. I'm going to multiply both sides by 2. Y squared equals 2/3 x cubed minus 2x squared. 2 times a constant is still just a constant, so plus c. Now, to undo the square, I'm not just going to take the square root. I need to do what? Not just the positive square root, but I need to take the plus or minus square root. And I'm going to get y equals plus or minus the square root of 2/3 x cubed minus 2x squared plus c. However, that's not okay. Your final solution needs to be a function, and the plus or minus makes this not a function. We need to pick one. How am I going to do that? I'm going to go back to that initial condition that I gave you, where I told you y of 0 equals -3. Now, if I want to be able to plug in 0 and have it equal -3 for a y value, I think I need to take the negative square root, because the square root always gives a positive answer. How are we going to get a negative y value? We're going to make it negative. We're going to choose one of those based on what our initial condition is. In this case, I'm choosing negative. Which means the general solution I'm going to focus on is y equals negative the square root of 2/3 x squared minus 2x squared plus c, all under the root. Plug in your initial condition, negative 3 equals negative square root of 0 minus 0 plus c. Sorry, you can't see that. Negative 3 equals negative square root of c, or 3 equals the square root of c. Square both sides. Your constant's going to be 9, which means the solution to this differential equation is y equals negative the square root of 2/3 x squared minus 2x plus 9. Things like this where you have to get rid of the square with the plus or minus square root and then choose one of the two branches, those have shown up several years on free response questions on the AP exam. Make sure this is in your notes. Okay, 2 more. Again, remember my goal is just to try to show you as many different variations on the algebra as possible. And most of these came from variations that have shown up on the AP exam. Do something a little different here. I want to solve this differential equation, and when I'm done, we're going to find y of 1. That last part shouldn't be a big deal. Once we have our answer, we'll just plug in 1. See if you can separate and see if you can integrate. And by the way, when you integrate, there should not be any natural logs. See what you can do. Separate, integrate, and then stop. You're going to get dy over y squared equals x dx. That's my separation step. Integrating 1 over y would give us natural logs, but 1 over y squared, that's just power rule. I'm integrating y to the negative 2 dy. On the other side, I'm integrating x dx. Integral of y to the negative 2, y to the negative 1 over negative 1. On the other side, x squared over 2 plus a constant. This is negative 1 over y equals x squared over 2 plus a constant. And now we need to start going into our algebra to solve for y. First, I want to get rid of that negative. Multiply both sides by negative 1. 1 over y equals negative x squared over 2. Constant times negative 1 is still just a constant. Just happens to be the opposite sign of what c originally was. I'm still just going to say plus a constant. Now, I need to do the reciprocal of both sides. The reciprocal of 1 over y is y. The reciprocal of this side, you are not allowed to do 1 over this thing plus 1 over this thing. You can't do the reciprocal of this plus the reciprocal of that. You've got to do the reciprocal of the entire side. 1 over negative x squared over 2 plus a constant. Y, don't copy this down, but you know that 2 plus 3 equals 5. Can I say 1 over 2 plus 1 over 3 equals 1 over 5? No, it doesn't work that way. But what I could do is say 1 over that entire sum, 2 plus 3 equals 1 over 5. We're doing the reciprocal of the entire side. Okay, I'm not okay with leaving the divide by 2 inside there, so let's multiply by 2. And we can get y equals 2 over negative x squared plus a constant. By the way, yeah, 2 times a constant is still just a constant. No point in saying 2c, let's just say c. See if you can find your c value. Plug in 0, set it equal to 1/2, get your c value. So 1/2 equals 2 over c. I guess I'll cross multiply. 4 equals c. Your solution is y equals 2 over negative x squared plus 4. Tell me what y of 1 is. I think this answer is going to be 2/3. There was another one I was going to show you, but I think I may hold off on that for a later video. This is our method of separation of variable. This is just going to take a little bit of practice on your end. You're going to try some homework problems. Tomorrow, very little bit of new material. A lot of tomorrow is just going to be a chance to do some practice with this stuff. Probably through Delta Math to get a little bit more, just kind of practice with this stuff. And that's all for today.